Hello again, everyone. Welcome back. And we hope that you've enjoyed the refreshment break just now. I'd like to allow a few more moments for all of you to be seated, and then we're going to welcome the next panel to the stage. Up next, we're going to have an insightful panel discussion to talk about Frontier in Science, Emerging Breakthrough. The session features distinguished SAR laureates and eminent scholars who share insights into groundbreaking discoveries that are shaping the frontiers of science. Now, please join me in welcoming our panelists and the session host to proceed on stage. They are Professor Nigel Hitchin, 2016 Shaw Laureate in Mathematical Sciences, Savilian Professor of Geometry Emeritus at the University of Oxford. Next, we have Professor Mak-Tak Hua, Director of the Center for Oncology and Immunology, Professor of Department of Pathology, Ka-shing Faculty of Medicine, the University of Hong Kong. Next, let's welcome Professor Matthew Bales, 2023 Shaw Laureate in Astronomy, Director, ARC Center of Excellence for Gravitational Wave Discovery, OSGRAV, Chair, Gravitational Wave International Committee, GWIC, Center for Astrophysics and Supercomputing, Swinburne University of Technology. And today we're honored to have as the host for the session, Professor Kenneth Yang, Emeritus Professor of Department of Physics, the Chinese University of Hong Kong. A warm welcome again, and over to you, Professor Yang.
All right. Good morning. Welcome back. So we have a distinguished panel of distinguished scientists, and we have been given the title to talk about emerging breakthroughs in science, emerging. I suppose we are supposed to gaze into the crystal ball a bit, or at least you are, to think about what breakthroughs might we see in the coming decade, even 2, 3, 4 decades. But before we get into that, perhaps I could invite each of you to give your insights, not yet about the future, but perhaps we could start by looking a bit at the past. Namely, when you chose the areas you worked on, major areas, 20, 30, 40 years ago, did you consciously think about what particular directions might be opening up? And what were in your minds? Were you well advised by your mentors, or did you stumble upon some major breakthroughs by accident, by serendipity, as it were? Who would like to start? Professor Bales, could you like to start?
Thank you. Yeah, I just did what I loved, and I thought being an astrophysicist sounded very cool. I had no idea that it would lead to lifelong employment, and I certainly didn't think it would lead me to win major international prizes. The prize I was awarded was actually for a serendipitous discovery of something called a fast radio burst. And fast radio bursts were about 1 trillion times brighter than any radio burst we'd seen in our own galaxy. And I don't think scientists had the vision or the hope that such things would exist. So it was a complete shock to me when we first discovered the first fast radio burst. And it actually seemed a little bit too good to be true. So maybe I'm not a good person to talk about the future, because my prize was for something that nobody had dared believe in. But when we found it, I think that the training I'd received from my mentors meant I could recognize the evidence and tell the difference between a spurious discovery and one that wasn't really there. So I think good training by experienced mentors is very important. But the reason I'm an astrophysicist is just I had a very deep desire to understand how the universe worked. And I was very gratified to see that the laws of physics could actually be applied. So the day I did force equals mass times acceleration, I went home and dismantled my bicycle and stripped it of all excess mass, so it would be easier to ride to school and back. So I really enjoyed being able to connect sort of mathematical relations to how things worked in the real universe, and I found that very satisfying, and I still find it satisfying 40 years later.
So would it be fair to say that it is not, or perhaps it was not in your case, just a matter of predicting or anticipating what would be the major breakthroughs, but being prepared for it and having the best instrumentation to catch whatever new phenomena might emerge?
Yeah, there's a nice saying which is, fortune favors the prepared mind. And I think whether I liked it or not, my supervisors were very good at insisting I tried to do good science and corrected my mistakes. But that training and decades of experience means that you can actually recognize a new phenomenon when you spot it.
Yeah. Turning to Professor Hitchin, if I may, just to take an example, I mean, you had some of your most important work was about the Higgs field, the Higgs anyway, which emerged, I suppose, in the 1960s in a sense. At least that's when the name first came up. But it didn't percolate into the mainstream consciousness of the physicists for a very long time. So how did those emerging new ideas came to your attention? Did you then recognize it as a field that was opening up with lots of opportunities and so on?
Well, my first encounter with the physicists was now in 1977, I guess, when there was a problem which, if you like, landed on my plate. I mean, I'd already been doing research for a while, but in various areas. And then there was this question about Yang-Mills fields, which had percolated from the physicists to a number of key mathematicians in the States, and they brought over to Oxford these ideas. And at that time, I was in the right place at the right time with the right background to actually start making progress. So, I mean, this was my first engagement with physicists, and it was a question of having the right physicists or the right mathematicians to translate what they were doing into something which was more amenable to the mathematician to handle. And so it turned out that there was a particular problem at the time. It was the problem what I call the instantons. And there were two of us collaborators with my thesis advisor, Michael Attia, and myself in Oxford. And then independently, or not entirely independently, two Russian mathematicians, Drinfeld, Manin. In those days, you couldn't travel, or they couldn't travel, certainly. But we communicated by mail. And we produced a formula, an explicit formula for constructing things. So that gave me an insight that somehow we should learn from physicists a lot more. But in that sense, it was the pure Yang-Mills fields, which and our resolution to a specific problem related to them, that led me to try and understand other types of these equations, and in particular the Yang-Mills Higgs equations. So this was where the Higgs field first came in, and for me that was my subsequent work. Then was on what are called magnetic monopoles, which were forms of Yang-Mills Higgs equations. And then on my own, I decided to work from 4 dimensions, which is where the Yang-Mills theory is, into 2 dimensions. And somehow the structure of these equations in 2 dimensions gave me something completely new. And so one of the things which I think the award was given to me was something which was at the time an observation. It was it was serendipity in a way. I had this structure, and there was a particular feature of it which was at the time an observation, but then gradually emerged as being something more foundational, not only in the original setting, but in a wider setting too. So in a sense, I was lucky to have been given at a key moment in my academic life a problem which I could solve, and gave me the confidence to go on and do other things related to it.
Well, you mentioned your supervisor, Attia.
Yeah.
And that obviously prompts the question, how important would you think having the right mentor would be? Because in case some in the audience don't know Atia, one of the giants of mathematics, differential geometry and so on, was having the right mentor a very critical step in getting into the right direction?
Yes, for me it was crucial, if you like, because of the way he adopted methods of doing research was very different. I mean, he wouldn't want you to go and read a lot of books in order to prepare for something. He was more leaping ahead, and once you encountered a problem, then perhaps to go back and try and fix it. But he was always looking ahead, being bold in his outlook, and reaching out to various different areas in order to advance. So, yeah, the collaboration with him, both at a doctoral level and subsequently, was very important for my life, and also for that of many others.
Thank you. Professor Mack, if I could turn to your work on, what is it, immune checkpoint protein, is that right, CTLA4? That was quite a number of years ago. Can you tell us how you recognize the field of immunology as a field that was opening up, having lots of opportunity? Was it just because there were new techniques opening up that were enabling new discoveries? How did it go?
Well, first of all, I'd like to thank, I'm sitting on the stage with, three giants in the field of physics. And the reason I'm sitting here is because at the University of Wisconsin, when I was studying physics, I failed. And I was kicked out. So I had to do biochemistry. But coming back to your point, I think discoveries are very, it's really, I think, 80-90% luck. You have to be the right time, the right place. It's almost like the stars all aligned. I remember I started in Toronto, and I had to join a department, and the leukemia department had a position, and they had the T-cell leukemia because other leukemias have been taken, and I know nothing about T-cells. But my work as a virologist, we were trying to understand how genes, if it's been a virus, and we adopted the method of subtraction. A virus that causes cancer, 4 genes. A virus doesn't cause cancer, 3 genes. 4 minus 3 equals 1. And so, I mean, my mathematics is as good as that. And we, identified several genes that cause cancer. So when I started at the T-cell, and I was told that the T-cell receptor has not been identified, and lots of immunologists were looking for it. So I read a paper by Alan Williams that said, if it's taken 20 years for people not to find the T-cell receptor, perhaps it's not immunoglobulin. So we did a subtraction hybridization with really good, talented postdocs, Japanese doctor, Yusuke Yanagi, and we were lucky. The CTLA4, it was technology. We learned how to do knockout mice from Klaus Rayavsky in Germany, and so we were just lucky to find the gene. And actually, I didn't know when we knocked out CTLA4, the mouse died because lymph nodes were everywhere. 20% of the weight of the mouse was lymph nodes. But Jim Allison said, if you make an antibody that blocks it, he can cure cancer. I told him he's crazy. But you know what? He was right and I was wrong.
So being in the right lab was an important factor in the story.
Yeah, I worked with Howard Tamman, Nobel laureate for discovering reverse transcriptase, and Ernest McCullough in Toronto, discovered hematopoietic stem cells. These people are, they think very out of the box, but in a very still pragmatic way. And I think that's very unique.
Yeah, thinking out of the box. Yes, Matthew.
He talked about luck, but I think luck doesn't help you if you're not ambitious. And I think it's very important to be trying to make breakthroughs and not just repeating what some second-rate scientist has done in another hemisphere. I think working for a mentor that has great ambition can be very inspiring, and trying to do radical things more often leads to breakthrough than just recycling the ideas of others.
Yeah.
And I think we all benefit from a well-resourced scientific community globally, and if you get enough ambitious people that are well-resourced with appropriate infrastructure, the discoveries will happen, and whether I discover them or my colleagues, sometimes that's a bit lucky. But I think without ambition, it doesn't happen.
Yeah, turning from the past to the future, could I ask each of you to gaze into the crystal ball and offer some guesses and advice as to what you think might be important new subfields in the next 20, 30, 40 years, relevant to the younger people here, and where there would be new opportunities? Nigel, you first.
Well, this is very difficult to peer into the future. I think there are changing features in mathematics. I think it's become more abstract, at least, perhaps this is a generational thing, that I think younger people now are more familiar with what we call category theory. I won't explain to the audience what category theory is, but nowadays the way in which theorems are formulated amongst a certain class of mathematicians is as what's called an equivalence of categories. It's at a very high level, and it's difficult for me to understand what the basics are. So I will give you an example that we're talking about breakthroughs. Then, if you like, breakthroughs in the past 10 years have been awarded. Well, as you well know, there's a parallel award program called the Breakthrough Prize. And the most recent one was in an area called Geometric Langlands Program. This is something which I'm, in some sense, the work which I made the award here has some relevance to, but the award in 2025 was given to Gatesker and his collaborators, and it's very difficult for me to perceive where in this, under all the papers that they've written on it, what I was doing becomes relevant. But I think this whole subject, the geometric Langlands correspondence, is a vast idea which in the past 10 years there's been quite a lot of different points of view. And I'm pretty sure that in the next 10 years there's a lot more that will be happening. But if we go back to the younger people, I think there's something here which is, I don't know whether it's a danger or whether it's an opportunity. But the issue of using artificial intelligence in mathematics is something which is being discussed a lot at the moment. And it goes hand in hand with formalized theorem proving. So, young people here will be familiar with ChatGPT and so forth. And so it's inevitable that when they're starting to do research, they'll be looking at this, and I think they'll need some guidance as to how to use this. And in mathematics, there are serious mathematicians who are saying that in 10 years, we will be using this to prove theorems, not necessarily taking what the AI gives us, because that may be wrong, it's known to be incorrect, but checking what it gives us in formalized theorem proving using computers as well. There are all sorts of dangers associated with this, in particular the use of, the power source. Some of these AI companies now, they're using as benchmarking for their procedures solving mathematical Olympiad problems. And I think the last 2025 Olympiad problems, I think 4 out of the 5 were successfully solved. But we don't know how much energy, how many computers they were using. And so this reliance on computers is dangerous, I think, in the sense that the mind has to understand what's going on as well as the computer. On the other hand, as I say, some of these ideas have become far more abstract than they used to be. So it's difficult for mathematicians to actually hold in their head these concepts. And it may be that a better interaction, a human-machine interaction, might actually help us to prove theorems, but not to rely on AI. But nevertheless, it's there. It's what we call, the elephant in the room. It's something there which we cannot avoid talking about.
Yeah, but I believe in our earlier correspondence, I think I found out you don't yourself do AI.
I don't at all. On the other hand, because I knew that the issue would come up maybe from questions from the audience or from the young people, then I did talk to one of my previous students, research students, who's now very much involved in this. He's involved in creating a library of theorems in their formalized form to be taken down, if you like, and used when your work demands it.
So in some ways, that's really the sort of venture for the next generation.
Exactly. It's something
that we are not well connected
not
to.
for me. And
it's a new language.
A new language, that's right. But it's in the future, I know, yes.
Professor Mack, your views into the crystal ball in the life sciences.
Well, Confucius said we all have 2 lives. The second one begins when we realize we only have 1. Medical scientists have 2 lives. The second one begins when you realize that immunology is the orchestra for all life symphonies. So I think from the point of view of what are the 3 things that are threatening humanity? Well, they turned 1900, the average age was 32. Today, the world's 75, and in Hong Kong, it's 85. So what are we going to get? We're going to get cancer, we're going to get Alzheimer. And the third thing that's going to threaten the world is there will be an antibiotic-resistant bacteria. We're all waiting for that, but that's not something I guess I am really qualified to talk about. But from the point of view from immunology, because cancer can be controlled by the immune system. How? We still do not know. And Alzheimer, my gut feeling is those immune cells in your brain over the years. There's a paper just came out that young blood cells can slow down the development of Alzheimer in old animals. So it's only the beginning, but I think it's going to be very interesting. But in any case, I think, to me, our laboratory is embarking on something which is a little bit more integrative. So in 2008, I was in New York at the Metropolitan Club, and sitting next to me was a neurologist. His name was Kevin Tracy, and he is absolutely brilliant. I said, wow. I said, what do you do? He said, I'm a neurologist. I know nothing about neurology, so I said, okay. Halfway through, after a few drinks, I said, tell me one thing that is crazy you don't understand. And he told me that Germans were stimulating nerves and the spleen moved. But that also, a lot of scientists found acetylcholine in the spleen and the liver. But there are no cholinergic nerves. So I said, well, why don't we work together? We'll make a mouse which is choline acetyltransferase green fluorescence protein. That's ChatGFP, not ChatGPT. Okay. Seriously. So we made ChatGFP and found out the T cells and the B cells were making neurotransmitters. And then, I don't want to bore you, we found out the liver regeneration, we found the gut movement, we found that infectious disease, all controlled by the brain to your immune system, even selecting your repertoire for your T cells. So I think this new lens may get us further into another level.
So almost a new paradigm about how things work in an integrated way.
Petty paradigm. I don't want to claim something that is not.
How about in cosmology and astrophysics?
I think there's two things that are driving revolutions in astronomy. One is the development of these multi-billion-dollar instruments, like the James Webb Space Telescope. This is something that the US spent $10 billion on. It's a remarkable instrument. It's got a 6-meter mirror. It's out in space. It can do some experiments 1 million times faster than previous Earth-based instruments in the infrared. And it's discovering what the universe looked like when it was very young. We have other instruments like the Large Synoptic Survey Telescope, which will scan the whole sky every few days and reveal so many transient phenomena that it's difficult to even catalogue them, let alone follow up each one. So we're kind of drowning in data, and we're turning to supercomputers in order to process it and sift through things. There's a great fan base for AI techniques in astronomy, but I also think there's a great danger that we will use it naively. And I've seen examples of students asking AI to do their PhD for them, and even submitting papers that a referee with a few minutes of thought has pointed out inaccuracies. And then when we've drilled back down, I had one student and I said, "What does this line in your software do?" And he said, "That's what ChatGPT typed out for me." I said, "You need to learn about unit tests and testing that what the AI is feeding you is actually correct." But my fear is they'll use AI to generate the unit tests and also get that wrong. So I think it's easy for older people to look down on new tools. I think AI is a great opportunity, but it's a great danger to our interpretation as well. And I would encourage all the young people here to take time to think. We're being bombarded by electronic screens, and people are swiping left and right and up and down, and our brains are not getting the chance to rest and renew. And I think the best thing I did for my career was take up long-distance cycling endurance events, and I would have to train for 4 hours, and I would just get on my bicycle and ride through forests and just have time to think without electronic warfare attacking me. So I think take time to think about what you're doing, not just respond every few milliseconds to a visual stimulus from social media.
Yeah. In case you don't know, I think we ought to congratulate the Hong Kong Science Park for having nice bicycle trails just outside. Highly recommended. But I guess what you're saying is that many opportunities will be enabled by new instruments. And that is where we ought to pay attention to. New instrument opening new horizons and new data available.
Yeah, I think we have laureates in our audience that use things like the Gaia telescope to catalogue the positions of billion stars. Reinhard used these remarkable facilities that ESO has created to watch stars orbiting the supermassive black hole. These are instruments that take decades of planning and different skill sets from maybe the people who use them to claim the glory. But investment in infrastructure and the engineering is vital to make the astronomical breakthroughs the scientists ultimately use. And if you understand the instrument and its limitations, it enables you to do breakthrough science that you don't always achieve if you're too much of an end user. So take time to talk to the engineers and understand what are the limitations to the instruments.
I'm conscious we are given only another minute or so before we turn to questions from the floor. So if I could just pop one additional questions to our panelists, and that is the following, that the number of likely breakthroughs in the coming decades is likely to be limited by definition of the word breakthrough. And there are thousands, tens of thousands of scientists all hoping to do important problems. So the hot fields are going to get very crowded. So how should young people position themselves to stand out in fields that are opening up and therefore crowded? And here perhaps I could turn to Professor Mack first of all, because certainly immunology, cancer, there are thousands of people working or claiming to be working on it.
First of all, for the field of immunology, don't believe in 80% of the literature. And that's why I don't feel threatened by AI, because AI is based on good science, and the field of immunology is still a mess. And the main reason is because it's so hot, everybody wants to jump in it without. But anyway, I mean, that means there's a lot of room for you. I just want to say there is a book by a guy named Simon Sinek. He actually spent some time in Hong Kong. He born in England, spent some time in Hong Kong. He's now, I believe, in America. His book is always starts with why. Why? And then how, and then what.
Thank you. Nigel?
Well, I would agree with this, that, I mean, as a mathematician, you want to understand why, how, and what. I mean, in some respects, you may be presented with a fact or a theory or a conjecture, but you want to dig deeper and to understand how it works or why it works. I mean, it's quite possible to be presented with a theorem which, okay, in the future perhaps may be proved by a computer, let's say, but you want to understand what's going on underneath it, what does it represent? And so the idea of digging down deep to the basics is something which mathematics is really somehow all about, being faced, if you like, historically with physical facts which you want to understand in some deeper fashion. So the spirit of, I mean, in order for young people to place themselves in such a position, it's in order to perhaps engage in breakthroughs in the future, I think it still comes down to the basic fact that you really want to understand what is happening and develop techniques to analyze that. But I don't think that's changed over the years, in fact, at all.
Matthew, would you have just a quick final word on this question?
Yeah, I think you need to look in the mirror and understand what you see and not try and be somebody you're not, and to get honest feedback about what your strengths and weaknesses are. I think you shouldn't be trying to win the Shaw Prize. I think you should be trying to act with integrity and maximize your opportunities with the talents you've been given.
Thank you all for your words of wisdom. We have another 15 minutes for questions from the floor, and the questions have already been, modern technology collected here. So I see a couple of quite interesting ones. Let me start with the following. Do you think the scientific community places too much emphasis on paradigm-shifting breakthroughs? How can we better value incremental but essential contributions? I suppose that is something that the Shaw Prize and other prize-giving bodies are guilty of. Emphasis on, breakthroughs rather than incremental work. Would any of you like to respond to that question?
I think the breakthroughs inspire us to work hard and try paradigm shifts. But the foundation of all of our science is the thousands of scientists and their papers that have preceded us. So I think the incremental work is essential, but it's not why I get out of bed.
Yeah, I think it's crazy, and it shouldn't be in the field if you're in the field for breakthroughs, because you're in the field for incremental understanding. But don't miss the opportunity for a breakthrough if you can smell it. Then take advantage of that smell. Listen to, once the most important thing is to listen. I listen everywhere, anybody, what they say. I mean, I told you in 2008, I listened to a neurosurgeon who was telling me stories of how nerves were stimulating. And most immunologists would say, well, no, but I listened, and it's very important.
With advice to young people, talk to people, listen to people, and we have arranged quite a few activities in this forum precisely for that purpose. On this point, Nigel?
On the incremental aspect, it's in mathematics. It is very important. Of course, if you're an editor of a journal, then you often get referees' reports which say this is incremental. This is not what we're looking for. There's a huge gap between paradigm shifting and the whole spectrum of achievement, which includes the incremental work. But so we should not denigrate incremental, the words incremental, if you like, even though in practice sometimes we do that in refereeing papers.
Now here's another question that is not quite the same. It goes like this. What advice would you give to someone who's passionate about a niche area that isn't hot, that isn't currently hot?
I say good on them. I think if you're doing what you love, at least you'll enjoy going to work. There's no point going to a hot area that you're not really interested in. But I do feel bad for students I sometimes meet, and they're doing a PhD, and I'm sort of pretending that it's interesting, and I'm thinking this is a complete waste of time, and maybe you should not be doing it. So, loving something is fine, but you have to take responsibility for what you produce at the end of it. And if it's a null result or something that you could have predicted with a few seconds of thought prior to the thesis being set, I do think we have a responsibility to set projects that gives our students an opportunity to shine and at least make an incremental discovery, even if it's not the breakthrough. But I'm wary of students without much experience thinking they're going to do something great without bouncing that idea off experts to get their opinion before they start.
So even in niche areas, talk to people outside that area and bounce ideas off experienced people.
Yeah, I also think you have to understand how you react to criticism. A lot of us are actually quite good at science, but the people who get in trouble are ones that when somebody goes, well, I think you're wrong, they have a meltdown. You've got to have the maturity and foresight to realize that maybe you are wrong, or the courage to defend your ideas.
Okay. And here's another question. Looking back, did you ever feel uncertain about the field you chose? What helped you stay the course or to pivot to another direction? Did that ever happen to any of you?
Well, yes, to me, it happened to me in my first year, my master's year, I guess, as a student. I felt I tried many different problems. None of them appealed to me. I mean, of course, I didn't make any progress in them, but they didn't appeal to me, and so I began to doubt my basic whether an academic career would actually be for me. And it was only towards the end of that period that I found a problem that I thought was interesting, that related to things I thought were further afield and would give me the opportunity of advancing in a broader area. And I made a very minor contribution with a little dissertation. And when I got the confidence that I could actually write something which was marginally new, then that gave me the impetus to continue. But it was not at all clear whether I should continue in academic research at that time.
Yeah, I have a slightly painful example. I'd done my PhD and I'd gone to the University of Manchester doing my first postdoc. I was given a whole lot of data, and I realized that the way we were reducing the data was very slow and cumbersome. And I had learned how to do something called a graphical user interface, which was quite new in the 1990s. So I sped up our data reduction by a couple of orders of magnitude, and I was very proud of myself. And my supervisor had promised me that the next paper we wrote, I would be first author, in recognition of my contributions to the infrastructure of the group. And we were timing neutron stars and when the pulsars arrived. And we started processing the last pulsar in our survey that we hadn't yet managed to predict the arrival times of the pulsars correctly. And there was a curious sinusoidal-looking pattern that was there. And we had a student working on it, and he managed to link the points, if you like, and we had this beautiful sinusoid going up and down. And we realized that this pulsar was being orbited by a planet. We were incredibly excited. And we thought about glory and fame, and the Shaw Prize hadn't been invented yet, but things like that, because nobody had ever discovered a planet outside the solar system. So we dashed off a Nature paper, because we knew other people were looking for planets, and got accepted, and we became very famous for about 6 months. And then one day, my supervisor realized that the way our 2 bits of software interfaced had a file which had a position in it, and it wasn't the same in both of these bits of software. And our planet was actually a mathematical approximation gone horribly wrong. And when he updated the position, an anti-planet appeared in the data. And then when he hit fit for the semi-major axis of the sinusoid, it went to 0. And we realized that despite all the media interviews and things we'd been doing and fame, that we'd actually made a terrible mistake. And so we wrote a retraction of our paper. And I'd have to say it wasn't a great time in my life. And I was thinking, well, there's my academic career gone. He actually got up at the American Astronomical Society and confessed his crime. And he was shocked that when he sort of took his last overhead transparency off, there was a standing ovation. People were very generous to him and our team. And it actually gave him the courage to continue as an astronomer. And I thought, if I leave now, it'll be because of a massive failure. I need to work hard to correct this fault and actually do something worthwhile. So yes, at that time I had a very real thoughts that I've really stuffed up here. And I think looking back, we were so keen to be the first to discover the planet that we didn't do the necessary checks that could have prevented this embarrassment.
Professor Mack, you have any experience in...
No.
No, okay. Thank you. Now we are open to questions from the floor. Please raise your hands and somebody would bring a microphone to you.
Hello, my name is Jeff from techchannel.uk. I want to know what's your views on the use of quantum computers in your fields? Is it good or bad?
I would say it's non-existent in my field at the moment, but people have great hopes for it. I don't actually understand how it's going to influence my area of radio astronomy. But I'm a little bit scared that the hype might outweigh the usefulness.
I have a former student who has a company now which is supposed to be doing quantum computation, but I think this is distinct from his academic activities.
Yeah, I think, again, it's just like AI. There are aspects of biology and medicine. There are lots of good data from which you can generate and kind of distill and come up with good, precise answers. But in many fields in biology, like neurobiology, I think is so complicated. Immunology is so complicated. I don't think there is enough raw data that is precise and accurate for something like a machine to distill and conclude with some really correct and distinct answers.
Over here. Over here.
Over there.
Hello. I guess my question would be, well, I guess your careers have worked out very, very well for you guys, but was there any advice that you would have given yourselves back when you were, for example, our age, as like early career scientists, that you would have wanted to know back then, or that you would have found very useful, I guess, when you were in our stages of our career?
Oh, double check any planets you think you might have discovered. I think working hard is not a bad thing. I'd say work hard in moderation. Like, I think if you have a burst of enthusiasm, why not do a 100-hour week or something if you're making great progress, because you'll love it. But I don't think you should think of, if I do 100 hours a week for 3.5 years or 5 years, that's going to end well. So I was a very impulsive student. I'd have some lazy weeks. I'd have some weeks where I'd do remarkably a lot of work, and it was because I just loved what I was doing.
I think it's your passion, what you really want to do with your life. Because especially growing up here in Hong Kong, I think that when I was growing up here in Hong Kong, my mother said, you be a doctor or you be a lawyer, otherwise I would disown you. So, you know, like, I mean, I'm still waiting for to be disowned. So you have to have that passion, because you're giving up a lot of other things, which may be very practical. And you're willing to take that passion to satisfy your own life. And then from there, maybe try to find a job that will pay you to reward you for your passion.
Yeah, I think that's true, the passion, but I think one should you may have moments of excitement. If you have a great idea, you think it's a great idea, it's good to let it mature a little, go for a walk, because you may find the next day that it doesn't work out. But understanding that it doesn't work out is progress. This is what I sometimes have to tell my students, that that finding out you're wrong is actually giving you knowledge. And so it's not really a negative aspect.
All right, I'm afraid we have run a bit out of time. Matthew, do you have a final remark? I see you have your mic.
Yeah, I would encourage you to work in teams, not on your own. And part of working in teams is behaving with integrity and contributing where you can and being trusted. And I think the relationships you form in your career are very important. And you want to be the person that, even if you don't get the big breakthrough, you say, they're a fantastic team player. Because being respected is actually more important than being famous.
Well, thank you all for all the input, advice, words of wisdom to the young people. It's wonderful we got a discussion going, and I hope the discussion will continue in the rest of this forum. There are many opportunities, and I hope you will make friends, talk to somebody in a slightly different field, and maybe some sparks will fly. Thank you.
Thank you. Thank you very much. Thank you so much to this panel. May we invite all the panelists together at the front of the stage for a photo. Please stay with us. We'll have one group photo. And ladies and gentlemen, let's put your hands together once again to thank this panel for the amazing discussions. A lot of great reminders for our young scientists, really. I'm sure they will benefit from them as they navigate their scientific journeys. Thank you once again. Please be seated. Truly inspiring. Well, as we wrap up this thought-provoking morning session, we have to extend our sincere appreciation to our esteemed show laureates, panelists, and participants for your inspiring insights and engaging discussion. We're also deeply grateful to all our distinguished guests and supporting organizations for the continued support and strong commitment to fostering dialogue, innovation, and collaboration within the scientific community. This concludes our morning plenary session. Thank you for joining us this morning.